Alright, today I'm going to try and convince you of the distance to the Sun using Venus and a bit of geometry. So to do this, we're going to use really just one assumption, that we live in a heliocentric solar system. If you're doubtful of this, I can go ahead and provide some examples. As well, we're just going to use some rules of geometry. And with this, hopefully we can convince you. So, a main point here is that we have the Sun here, which I'm going to label with an X. Then we have Venus on a smaller orbit around the Sun than we are. And then we have Earth's orbit at a larger point. Now what I'm going to say is that we have the Earth here and Venus, which let's do pink because that's fun. We can make measures of its angular position relative to the Sun. So one point, it might be here, under which case we would see no angular difference to the Sun. And we can make another measurement at a later date. And here we're going to be able to measure some theta, but we're not going to stop there. In fact, we're going to keep doing this measurement and keep doing it and keep doing it until we find some maximum angle, which is going to look something like this here. Now, since these orbits are roughly circular, what this means, let me just draw this a little more solid here. What this means is that where this intercepts Venus's orbit, it's the tangent line of a circle. And what we know from geometry is that then if we take a line from this point to the center of the circle, this line here is 90 degrees. It's perpendicular to this line we just drew in black. Okay, so why do we care about this? We're going to label this edge here to be 1 AU, 1 astronomical unit, and we want to know the side length here. We want to know x in terms of astronomical units. Okay, so we have a right angle triangle. So this is pretty easy for us to do. Important note, yeah, so when we find this maximum angle, let's call this theta m. So we have that from trigonometry, the sine of theta m is equal to x over 1 AU. And then we can solve for x. So, what is a reasonable measurement for theta m? This is something anyone can do with a telescope if they want. They can just get a little filter that makes it a little easier to look in the daytime. And you can measure this yourself to be theta m approximately equal to 47 degrees. And we're going to be pretty generous throughout all of this, so we're going to say we're not that great at making measurements, and that this is plus minus 10% of the true value. So we're not sure which way, but it's something. And if we write this as an absolute uncertainty, then this is 47 plus minus 5 degrees. Okay, so that's our first measurement we've made. Now, from this, we can calculate what x is. Let's do this in a new color. Okay, so x then is just sine of 47 times 1 AU. And this is, I calculate this to be about 0.73 plus minus 0.06 AU. Okay, I did ask if you knew how to do propagation of errors. I didn't see a response there, so I'm just going to assume you know, or you roughly understand the procedure. Otherwise, I can explain that later. This is the only really tricky one, if you haven't seen it before, is the error in the trigonometric function. But we can do that if you want. Okay, good. So this is also a nice point because when we have, let's do this in orange here. So when we have this point in Venus's orbit, it's very easy for us to then find the period of Venus around the sun for when it comes back to this point. So you can also, if you want, you can make a calculation for the period of Venus from your own backyard if you're feeling up to it, or we can take someone's measurement for us. So I did this and I found a period of 225 days, but again, we're just going to assume that there's a 10% error on this if we were to do it ourselves. So let's write this as plus minus 23 days. So this is our period. As well, then we can find out its angular velocity. So we can get that omega is 2 pi over this. I'm not going to write the uncertainty, but I'll write it at the end after the propagation. Over 225 days. I'm going to convert this to seconds behind this, but like behind the camera. And this works out to be, where do I have it? Here we go. 3.2 times 10 to the negative 7 radians per second. Here, let me write this a little differently. I have this as being 3.2 plus minus 0.3 radians per second. Okay. Good. Now, this is probably the most tricky measurement, but it's again a measurement you could do in your backyard with a friend, albeit your friend's going to be a little lonely because he has to be kind of far away from you. So here is the Earth. Here's Earth. I'm going to draw it as a circle, but if you want, you could draw it as a flat plane. In fact, let's do that for you. So we have a flat plane. And then here, I'm going to try and draw a better circle than last time. Here is a small cutout of Venus's trajectory. So what we do is, on Earth, you and your friend are going to spread out. It doesn't really matter how much you spread out, just as long as you do, and that you know the distance. I'm doing this as if we're on a non-flat surface, so I'm going to do the diameter of the Earth that I know. You can plug in your own values here if you want. So I'm going to write this as the letter D. And in fact, I want to switch colors again to maybe a dark blue. So letter D. So I believe D to be 6,371 kilometers. I realize I didn't write down an uncertainty for this, so, we'll just write it here. That's going to be about plus minus 600 kilometers. I'm still doing 10%, but, that's probably not super reasonable based on my belief of this number. Okay. So, yes, you have your two friends, and one's going to stand on one edge of this plane, and the other one stands on this edge of the plane. And what's going to happen is Venus is going to come along in its trajectory. Do we go faster or slower than Venus? I can never remember this for some reason. Let's say it goes faster. Sure. So Venus is going to come along in its trajectory this way, relative to us. And observer number 1 is going to see Venus at about this point as transiting the sun. Now, this could be transiting the left-hand side of the sun, the right-hand side, or the middle side. It doesn't matter as long as our two observers are consistent. And he's going to see this at time 1. And then at time 2, observer number 2 is going to see the same transit. And they see them at slightly different times just because of parallax. They're a distance apart, and we're a finite distance away from the sun. Now, all the other ones, yes, what am I saying? Okay, so you make these measurements of T1 and T2, and then you find a delta time, and you will probably measure this to be about 2 minutes. Again, we're just going to say 10% error, so this will give you around 120 plus minus 20 seconds. I think I made this slightly larger because this is probably the hardest uncertainty to make, so we're going to even say it's 20% almost. Okay, so this is cool because this is, all the numbers we have now is going to let us make a measurement of this distance here that I'm going to write as capital D. So this is capital D is equal to the angular velocity times the time that it arced out times the radius. So we have omega up here with some uncertainty, we have our time with some uncertainty, and we have our radius, which is this x value here. So we can go ahead and put those in. When I do this, feel free to check. I get 3.0 plus or minus 0.6 times 10 to the negative 5 AU. I think if you convert, well, we shouldn't convert yet because we're not sure what an AU is. If you wanted to check that this number made sense, you could plug in your expectation for AU here, and I think you'll get something around like 4,000. So, so far we're in kind of the ballpark. Okay, why does all of this matter? It matters for more geometry reasons. What's a nice color? Maybe a dark green. Okay, so these are very small angles in the sky. And, whoa, okay, well, whoops, not sure what that was. Okay. Oh, interesting. I seem to have a bad, okay. Interesting, we have to go in the other direction. Okay, so we have one large triangle here with this distance being d, the size of Earth, obviously drawn in exaggeration. And then we have another, let's do it in red, Christmas tree colors. We have another triangle about size, slightly smaller, right? And we know that this large size is 1 AU, and we know this smaller size is something like 0.73 AU, 0.73 AU, A3, AU, and now we know that this distance here is something like 310 to the negative 5 AU. And the reason this is useful is because of geometry and similar triangles. So, what we have is that 1 AU over the distance d is equal to 0.73 AU over this number that was called d up here. And so now we can go 1 AU is equal to d over capital D times 0.73 AU. And all the units are going to work well here because this capital D we know to be in AUs, and little d here is in kilometers because that's how we measure it on Earth. So what we get is that 1 AU, after you do the calculation and all of your uncertainties, you're going to get 1.6 plus or minus, let's call that 0.4 times 10 to the 8 kilometers. So, okay, let's write this in one other way because this is maybe not super clear. This is 160 million kilometers plus or minus 20%. So just to be clear, 20%, that's saying that our lower bound on what an AU is in our measurement is that 1 AU lower bound could be at minimum 1.2, whoops, let's maybe write this the same way here, 120 million kilometers, and it could be at most 200 million kilometers. So obviously these numbers are different, and you might say, oh, that's horrible, but on the scale of solar systems and universes, really a lot of what we're concerned with is scale of things. And really what we're interested in is the fact that we're talking about hundreds of millions of kilometers, right? So, you know, we're not talking about thousands of kilometers. We're not talking about tens of thousands or hundreds of thousands. It's really hundreds of kilometers. I can't even write it. Hundreds of millions of kilometers. Yep, that's, I think, all I wanted to show. I'll just scroll through this in case you want to review anything here. But I think all of these assumptions are very reasonable. They're all measurements that you can make with a telescope in your own backyard. 10% error, I think, is very reasonable on all of these things. The time one I could see being a little tricky, but 2 minutes is quite a bit of range to make that measurement. Yes. Okay. This is the first time I've done this calculation in about 5 years, maybe 6 even now that I think about it. Because of COVID, that took up a lot of time. So maybe I've made a mistake here, and if I have, I'll correct it and re-upload this. Yeah, thank you, and I hope this convinces you.